Hi, my name is Cole Appen, and this is Physics 2211 Lab 4 Oscillations. Introduction. So the purpose of this experiment was to observe the oscillating motion of a mass attached to a spring, then create a computational model that predicts the same motion, and compare the observed motion to the predicted motion. Also plot the changes in the energy that occur during the predicted motion. The results. The observed motion and predicted motion are fairly similar in both the x and y axis. Main ideas. First, Newton's second law, or the momentum principle. The net force on an object is equal to the change in the momentum over the change in time. You can see it in the formula. And then we'll also be using the velocity and position update formulas. The final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. And then for the position update, final position is equal to the initial position plus velocity average times the change in time. More main ideas. The energy principle. The change in energy of a system is equal to the work done on the system by the surroundings, in addition to the exchange of thermal energy between the system and surroundings. So delta E is equal to work plus Q. We will also be using the translational kinetic energy, gravitational potential energy, and spring potential energy formulas here. So the system and surroundings. In this case, the system is the spring, the mass, and the earth, and the surroundings are nothing. So to find the total change in energy, we'll add the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. As you can see in the free body diagram, the spring force is opposing the gravitational force. The tracker data. Here we have the tracker data. So the mass was 0.402 kilograms, the initial position negative 0.0472 and negative 0.689. Initial velocity is 0, and it ran for about 9.9 seconds. Computational model. So to find the delta t, we have to find how much time was in between each frame, which ended up being 0.095 seconds between each frame. That's our delta t, and then the initial conditions are the same as the tracker video. The equations. So first we have to calculate gravitational force, which is just the mass times the gravity. Then we calculate the spring force, and then calculate the net force. Then we're using the momentum principle to update the object's velocity and update the object's position. Then we have to find the kinetic energy, gravitational potential energy, spring potential energy, and then the total energy. Oops. Here's the computational model result. Green is the spring potential energy, and then red is the gravitational potential energy. Blue is the change in kinetic energy. So all of these add up to the total energy with change in energy, which is the orange line. And then as you can see, this is the blue is the predicted motion, red is the observed motion. In both the x and y, they're off by about the same amount, which makes sense. They're pretty close, pretty similar. In conclusion, what does it mean? Is the energy principle satisfied in the computation model? Yes, the energy principle is satisfied, as adding up all of the changes in energy, we get 0. As you can see, the orange, the total energy is 0. It does not change. For the other what does it mean question, we had to estimate the oscillation periods from the x and y position tracker data. So in 4 oscillations, it took 6.48 seconds for the x, divided by 4, we get the period, which would be 1.662 seconds. And then the y position, we did the same thing, found it was 1.59 seconds. The difference between these is about 0.4143 seconds.